Okay, I suppose the volume is fine. So, uh, good evening. I'll get started. I welcome the viewers to this problem solving and live interaction session for the subject strength of materials offered by Professor K. Ramesh on the Swayam portal. So, today we will be discussing the contents of week 11, which has some rudiments of the deflection, beam deflection by superposition, etc. And then a general introduction into the theories of failure. So, for those who are watching this for the first time, I'll just briefly introduce myself. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at the Indian Institute of Technology, Madras. And I'm working under the guidance of Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So, with that, perhaps we'll get started. Are there anything that we need to discuss before we get started, Mr. Jayakrishnan? I suppose you had asked me a couple of questions. I have taken note of them. So we will be having one additional session week after next, which will be the concluding session, so to speak, which will envelop everything. So I'll try to cover the most unanswered questions in there. So I suppose you can bear with that.
Sure, no problem.
Okay. Okay. All right. So in that case, let me get started. So let us look at the first question of the day. It says if sigma 1 is greater than sigma 2 is greater than sigma 3, are the positive principal stresses at a point, and sigma ys is the yield strength of the material in tension, then according to the maximum shear stress theory, failure occurs when which of these happens is what is asked. So basically we have been told that sigma 1, sigma 2 greater than sigma 3 and all are positive. So in general, so material failure is characterized by or rather material itself, material behavior is characterized as in two broad forms. So one is where it is hydrostatic pressure insensitive and then hydrostatic pressure sensitive. So we know that a general stress tensor can be decomposed into two actions. Basically, one is a isotropic or a hydrostatic pressure. The other one is a deviatoric pressure. So there are certain classes of materials which are insensitive to hydrostatic pressure, and these basically we term them as ductile. And here failure is governed by shear stress, basically distortion. So here theories of failure will be functions of our deviatoric stress tensor. And here generally we see these are what we generally term as brittle, and here it will be function of the actual pressure, the maximum principal stresses and so on. So it is not universal that one material will behave in one of the either fashion as listed here. It is also a function of temperature and many other things. So in general, we see that metals follow under normal operating temperatures. They show a ductile behavior. So we generally have there have been many theories that have been propounded to predict or to estimate the safe loads for these metals, namely some of them that are von Mises and Tresca and so on. So one of which depends on the maximum shear stress, one of which depends on uh, the some invariants of the octahedral shear stress and so on. So these will come under the ductile category. Whereas the brittle category, we know the maximum principal stress. For example, the example of a chalk that is taken, limestone that is taken, it fails in a brittle fashion when the maximum principal stress is exceeded in one of the principal planes. So that is where the maximum principal stress theory and other theories like Moore Coulomb theory and so on, all these will come under the brittle criteria. So just a broad introduction of how pressure sensitive and pressure insensitive are categorized. So basically, if we see the maximum shear stress criteria is something that is widely applied to metals, which is also known as the Tresca criteria. So with this background, if we see, we have been told that there are three principal stresses and all of them are positive. So if we were to draw the Morse circle for this case, so we have the axis like that. So this is sigma and this is tau, say, and then we have three positive principal stresses. Let this be sigma 1, sigma 2, and let this be sigma 3. Just for example, I'm taking. So this is sigma 1, this is sigma 2, and this is sigma 3. So if I were to join these two like that, so this is the Moore circle in the 1, 2 plane. Similarly, we have the 2, 3 plane, and then here we have the 1 and 3 plane. So this is the three-dimensional representation of the actual stress state that has been defined in the question, where the principal stresses are sigma 1, sigma 2, sigma 3, with all the principal stresses being positive. Now, the maximum shear stress theory states that a material is deemed to have failed if the maximum principal stress, if the absolute maximum, not principal stress, sorry, shear stress exceeds that in the case of a simple uniaxial tension, in the case of uniaxial tension. So basically what we try to do here, generally there is no necessity that our loading conditions should be such that our material will always experience only uniaxial tension. Naturally, there will be other components that will come into play. But a convenient way to characterize this is we compare the combined effect. Given that we know our a method to actually calculate principal stresses, so our aim is generally to use these principal stresses and arrive at one quantity, which can then be compared to a normal case of uniaxial tension for the same quantity, that is. So if this is what is taking place in the actual structure that is being considered, in the case of a normal uniaxial tension, for a for the case of uniaxial tension, we know that sigma 1 is just the axial tension that is taking place. Now, since we want to push it to the limit, the limiting condition would be a material, and we are dealing with a ductile material. So as soon as it yielding sets in, that is when we deem the material to have failed in its functionality. So at that limiting condition, sigma 1 would actually be sigma y, the yield stress of the material. And sigma 2 and sigma 3 will be 0 in the case of a uniaxial tension. So if I were to draw the Moore circle for this case, what does that come out to be? So again, this is sigma and this is tau. So let me say that This is my sigma y. So if I draw the Mohr circle like that, this is the case of a uniaxial Mohr circle for a case of uniaxial tension where it has been loaded to such an extent that it has reached the point of failure, beyond which it is no longer functional because sigma maximum has come to sigma y. So in this case, we know that the other two Mohr circles are basically dots at the origin because the other two being zero. So you can naturally see that these are just simply points on the origin. So in this case, what is the absolute maximum shear stress that takes place? It is nothing but the radius of this circle. So the absolute maximum shear stress in this case is nothing but sigma y by 2 for the case of uniaxial tension. Whereas here we can see that depending on the values of sigma 1, sigma 2 and sigma 3, that is if sigma 3 is negative and so on, we will have to consider the maximum, the absolute maximum shear stress will be the radius of the biggest Mohr circle there is in this case. So for this case, we can see here the absolute, or rather let me write the shear stresses first. The shear stresses in each of the planes can be written as one will be sigma 2 minus sigma 1 minus sigma 2 by 2. Then we have sigma 2 minus sigma 3 by 2. And then we have sigma 3 minus sigma 1 by 2. The absolute value of these is actually the radii of each of the three Mohr circles that we have. Now, which will be the most governing of these? We actually have to take the maximum value of these three. And this, when it exceeds, what happens in the case of uniaxial tension, we deem our material to have failed. So we have the working stress here, the sigma 1, sigma 2 and sigma 3 being a function of the working stress, that is the stress that is applied on the material, on the actual component. And then we have the component made of certain material, which based on testing we have found that it fails at some sigma y is the material parameter that we have. And this theory states that the material is deemed to have failed when the absolute maximum shear stress exceeds that for this material in the case of uniaxial tension. So this is what is our maximum shear stress criteria, also known as Tresca criteria. So this is a general statement. In our case, specifically, we have been told sigma 1, 2, 3 is in the algebraic order. That is how we will be writing. So in this case, it is easy to see that this will water down to this quantity alone. This quantity, when it is greater than this, we can say that failure has occurred. So let us look at the options. So we have sigma 1 minus sigma 2, 1 minus 3, and then 1 by 2. So this is clearly not the answer. So out of these two, we can see that one actually says, one actually shows a condition where the working stresses are below the yield, below the maximum yield stress in the case of uniaxial tension, which happens to be the safe condition. So this is the safe condition where it is acceptable. Whereas as soon as it becomes equal to or greater than that, we consider the material to have failed or the component to have failed. So the component fails. So sigma 1 minus sigma 3 by 2 when it exceeds the maximum shear stress in the case of uniaxial tension for that material of which the component is made is considered to have failed. So I hope this is clear. So along similar lines, we have actually saw the maximum shear stress here. Another theory is actually relating to the octahedral shear stress, which is called the von Mises theory. So I will just be stating the formula here, but the derivation for which can be easily derived, and it has also been done in the lecture, so I'll avoid that jargon here. Anyway, we will be seeing as we go about on how to apply these. Now, this is the limiting condition that we have been given for the material. This is a function of the actual stress that has been applied, but we don't want it to always reach the peak stress. So we would also want to bring in some factor of safety, factor of redundancy, because of many other parameters about which we are ignorant. Because we generally take a rod of steel, let us say, and then we will be loading this in the universal testing machine in order to determine our sigma y. Whereas the same structure, if there is a structure made of steel, we are extrapolating the material properties of this rod to the actual structure. So there is some approximation involved. So considering all this, there are certain steps where we will be bringing in some factor of safety. So generally, we will not be comparing it to this value, but a factored value of this. So this will be multiplied by some factor here, which will be obviously less than 1 in order to compare it with not maybe 100%, but 80% of the value and so on. So when we multiply that, we will be having a factor of safety that will come into the picture. So in general, given a material, given some yield stress and a factor of safety, we will be asked to design the component for some working stress, from where we can either calculate the actual permissible stress that can be allowed on the component, or we can actually design the section of the component such that the stresses are within the limits, within the factored limits. So I hope that is clear. And again, since in the interest that we don't forget the history of how the subject has evolved, so they have asked a question to match the actual theory and the person and the scientist who has propounded that. So this is merely an activity of memory. So you can just revisit the lecture once. Actually, maximum principal stress uh, is the actual criteria which was uh, initially in the development of material science. So maximum principal stress was what was considered to be the governing criteria for quite a number of years before people explored more and found that there are pressure insensitive and pressure sensitive materials. So maximum principal stress was developed by Rankine. And then we have the shear stress theory about which we just discussed, which was propounded by uh, Tresca. And the maximum distortion energy theory, another way to put it is the octahedral shear stress theory, which was what was propounded by von Mises. And the elastic energy theory was propounded by Beltrami, and so on. So you can revisit the lectures once in order to find what the correct answer is. But this is just to give a flavor as to if we associate with the person and the timeline as to how this has evolved, it will give a better appreciation of the subject. So that is the spirit behind this question. So I hope you take it in the spirit that it is intended. Okay, so let us look at this question. So consider a beam of length. We can see that this is a propped cantilever beam. So we have a beam that is fixed at end A, and at end B we have provided that with a prop, a hinge, in order to arrest the deflection at the free end of the cantilever, so to speak, at point B. And this is subjected to a uniformly distributed load of 4 kilonewton per meter. And the length of the beam is given to be 3, so I'll just mention it here. So this length is 3 meters. So this much we have been given. Is subjected to UDL as shown in the figure. Determine the magnitude of the reaction at point B. So given this uh, beam and the prop, what is the magnitude of the reaction at point B? Now we can see that when we draw the free body diagram of this structure, we'll be seeing there is a reaction at A, and then there is a reaction at B, and then there will be some reactionary moment at C. So there are already three unknowns here, whereas we have only two equilibrium equations at our disposal, because the horizontal one just leads to 0 equal to 0, which is trivially satisfied. So we can clearly see that this is a statically indeterminate beam. Here we cannot determine the reaction by the principle of statics alone. So we need to bring in the deformation picture, which is what we will do. So now let us say that we have the beam like that, and this is fixed here. So I'll just, let me take it like that. Okay, so it is fixed over there. And we have the uniformly distributed load, which I'll just represent it like this for the sake of convenience. So this is some W, let us say. So under the action of this load, this beam would have deflected something like that. I'm just drawing an exaggerated picture for us to be able to appreciate that this would have been my deformed shape if there were no prop here. Whereas if I were to take the same structure, I'll just remove the UDL from here, and let us say that instead of the prop being there, there is some essentially the prop is providing some reaction at that point. So let me actually add that reaction like that. As an external force, let RB be that reaction. So we can see, or let me remove this. Under the action of this load, this would deflect something like this, something like this. Just to appreciate the deflection, I'm drawing it as an exaggerated picture. So we can see that once we have a cantilever and we load it with W, it goes down by certain amount because of the deflection of the free end. Whereas if we were to prop it and consider that reaction alone, so it will be deflecting somewhat in this manner. Now, if we were to superimpose these two together, what is the end result? Depending on how much reaction is mobilized, there will be some residual deflection at the bottom. Naturally, the reaction cannot exceed the applied force and overtake it to take it up. So naturally, the deflection at the free end, or the propped end, I should say, the deflection at the prop can at best can be 0 or something because of this load, some non-zero value because of this load, depending on how rigid our prop is. So in this question, we have been shown that it is actually firm ground. So here, what this implies is the final deflection due to the action of W and the prop together brings the deflection at point B to 0. So let us draw the final picture where I have the load as well as the reaction. In this case, this will come to 0, or rather I should. So the deflected shape, naturally there will be no slope here. It will go something like that. And then this will bring it back to 0. So this is the final deflected shape, which can be considered as a superposition of these two cases. Now we know how to calculate this quantity by our fundamental understanding of beam deflections. Same goes for this quantity where RB is some unknown, and these two nullify each other in order to bring the deflection to 0 at the free end. which is our additional equation using which we can actually find out what the value of RB is. So let us go ahead and do that. So I'll consider each of the problem separately, and then towards the end let us add it up. So considering this problem for the free end, let this be some delta 1. I'll call this some delta 1. So for this problem, I know that my bending moment diagram is it's a parabola, something like this. So this is my bending moment diagram. So this is MB at the free end. Now I know if this is W and this is L. So what will this quantity be? It will be WL into L by 2. So WL squared by 2. So this is actually WL squared by 2. But to apply our moment area method, I need to scale down the bending moment diagram by EI. So let me just do that. I'll operating under the assumption that this beam is prismatic, where EI is constant. So I can simply divide this by EI. So this is not bending moment, but this is my M by EI diagram. So far, so good. So I have this as M by EI, and this I know it is the length L. So what is delta 1? I know that the tangent drawn here goes straight, and the tangent drawn at the free end. So actually the difference between the two, when I take the moment of this M by EI diagram about the free end, I will actually be getting delta 1. So using the moment area method, so delta 1 is nothing but area, moment of area of M by EI diagram, MB by EI diagram about point B. Actually this is A and this is B, so about point B. So let us go ahead and calculate this. So delta 1 is, what is the area of this parabolic spandrel? If this was straight like this, it would have been half. It would have been half. Since it is a parabola, it is actually 2/3 of 2/3 into the height, that is 2EI into L. So this is the area. The centroid of this will be somewhere over here, and this distance you can actually look it up. It will be 3/4 of the length. So this will be into 3 by 4 into L. Yeah, see, if we were to take a rectangle like this parabola will actually be occupying 1/3 of this area, and the other one, the other parabola will be occupying 2/3 of the area. So actually this will be 1/3 of the actual area of the rectangle, which is WL squared by 2EI into L. 1/3 of this into the distance of the centroid from the end B, which is nothing but 3/4 of L. So if we were to solve this out, this will be WL power 4 by EI, and then it is just a matter of calculating the coefficient. So this will be 1 by 8. So WL power 4 by 8 EI is delta 1. So therefore, using our moment area method, we have calculated this to be WL power 4 by 8 EI. So far, so good. So let this be marked as 1. Now I want to superimpose this with this quantity. So let us go ahead and, I mean, it might be overkill to actually be calculating all this, but at least if we do it for a couple of problems, then we don't have to actually remember that table of deflections. We can actually derive this from first principles anytime we want. So in this case, we know that our bending moment diagram simply a rectangle like that. So this will be MB, which is RB into L. So this is RB into L by EI, because I'm actually calculating the M by EI diagram, and then this is L. So let this be delta 2. Let this be termed delta 2. So therefore, again, I'll just take this statement. Yes, so using the moment area method, delta 2 is actually moment of the area of M by EI diagram about point B again. So this comes out to be delta 2 is half the area, or the area of this triangle, which is half into RBL by EI into L into, we know its centroid is at a distance of 2/3 of L, which is nothing but 2 by 3 into L. So therefore, delta 2 comes out to be RB L cube by EI, and then I'll just calculate the coefficients. So this is half and this is 2/3, so this is just 1 by 3, which is a famous expression that we know, RL cube by 3A or PL cube by 3A. This is the most fundamental of all deflection formulae that we know of. But it is good to derive this from first principles at least once. So we have this as 2. Now our idea, in order for us to obtain this configuration, is just to superimpose these two. Now naturally we can see delta 1 is towards the bottom, delta 2 is towards the top. So if I were to equate the absolute values of these two, I'll be able to get an equation from where I can actually find out RB. So let us go ahead and do that. So this is actually equal to this quantity. So from here, so equating 1 and 2 such that deflection at D is equal to 0. So that is what we have done here. So RB, from here we can see, so EI just cancels out. So this gives us RB is nothing but 3WL by 8. So although we brought deflection into the picture even without knowing the section, we have been able to find out RB, which means that for a prismatic section, no matter what the section is, this ratio is not going to change as long as we respect these boundary conditions. So it is nothing but 3WL by 8. So therefore, if we were to plug in the values, so W here is given to be 4 kilonewton, the length is 3 meters, and the reaction at B is what is asked. So this is 3 into 4 into 3 by 8. So which comes out to be 4.5 kilonewton. So this is the actual reaction at the propped end. So now that we know this, we have for the other reactions, we have our principles of statics at our disposal. So when we sum up Fy equaling 0, we will have the load, we have Rb and we have Ra. Rb we just found out using our compatibility of displacement of deflections at point B. So Ra is nothing but 4 minus Rb and so on. So once this is known, if we equate moment equilibrium, we will be able to find out the fixed end moment as well. So everything about this beam is known in that case, which I'm not doing here, but it is something that you can just attempt. So we've been able to find out Rb using the principles of our basic understanding of how deflections work, and we have actually superimposed two results, two simple results which we could deal with individually in order for us to find out what the reaction at point B is. So I hope this is clear. If there are any questions, please feel free to ask. In the meantime, I'll move on to the next question. Okay, so let us look at this question now. Consider the arrangement of identical beams. So there are two identical beams here. We are able to see, out of which one beam has a fixed end here, and then it is connected to a roller. So mind you, this is a roller, and this roller is placed such that its center lies on the beam of a at the center of a simply supported beam at the bottom of it. So, and these two beams are identical, with made of steel and section such that this is 200 and this is 400 mm. So width and depth is given. So it's a rectangular beam. These are rectangular beams, out of which one is a cantilever and one is actually a propped cantilever, so to speak, beam CD, and beam AB is a simply supported beam. So consider the arrangements of these identical beams as shown in the figure and report the magnitude of the following quantities. So what are the quantities asked? Reactive force at point C. So at point C, there will be some force interaction. So we want to know what is the reaction that is offered by beam AB onto this beam at point C. Deflection at C is asked, the reaction force at A is asked, and the reaction force at D is asked. So the reaction everywhere and what is the deflection here is what is asked, because at the other points we can naturally see that deflection is 0, this being a fixed end, and these two by virtue of being supports, the deflection is 0. Now how do we go about solving this question? So if I were to take this, if I just take this piece here and let me just put the beam over here. Now if this was a roller that is resting on solid ground, if this was the case, then we know it is similar to our previous question. It is similar to previous question except there is a roller here which is sitting on firm ground. So again our deflections would have been 0 at that point, and by simple superposition we would have been able to find out the reaction. So for this case, if this is C and this is D, I hope that is how it is labeled, yeah. So this would actually offer a reaction RC, right? And if this was sitting on solid ground, we know how to calculate RC. So RC would have been 3WL by 8, as we saw. But actual configuration is not this way, because the deflection due to the load W and the deflection due to our RC does not equal 0 in this case, by virtue of this beam having some flexural stiffness, or rather having some being deformable, so to speak. So this will actually have a deflection like that in an exaggerated scale I'm drawing. So the actual support would go down by this much. It will not be 0, By virtue of this not being a solid floor but a beam, the beam would have some deflection. So here it actually, or rather let me take this beam first. So this will actually go down by some amount like that. And by virtue of symmetry, the maximum deflection will be at the center. So this quantity is delta 3, let us say. And we already know for this beam, if this doesn't sit on the prop, the actual deflection will be something like that. So this is delta 1 plus, and I should actually remove the roller here. That is when that will be delta 1. So this plus, let me just take the beam alone here. And I'm disregarding the load here. So I hope you're able to bear with that. So if there is no load, but only a reaction, if there is only a reaction at C, naturally this will have deflection like that. Let this be delta 2. So the only difference between this question and the previous one is delta 1 minus delta 2 was equal to 0 in the previous case, whereas here it won't be equal to 0, but it will be actually equal to delta 3. So this is the only compatibility that the configuration should respect, and rest is all straightforward. So this is our actual governing compatibility equation. Which needs to be respected in order for us to calculate. So delta 1, since we have already derived it in the previous question, it's an overkill to do it right from first principles again. So delta 1, we already know it is W alpha 4 by 8EI. We just saw how it came about. Over here, we just saw it was W alpha 4 by 8EI. Only the beam is flipped now about the vertical, so that the fixed end is at the right side rather than the left side. Rest everything remains the same. So delta 1 still remains the same. Delta 2 also remains the same, except that this is not RB but it is RC, depending on how we label the points. So delta 1 and delta 2 can be read out from the previous question itself. So from the previous question, we can actually take these equations. So delta 1 is this. Similarly, delta 2 is this, with the minor change that it is no longer RB, but this is RC. So I hope you are able to appreciate that. So delta 1 and delta 2 we already know. Now it is just a matter of calculating delta 3 and then putting them into this equation in order to calculate rest of the quantities. So let us go ahead and calculate delta 3 first. So for calculating delta 3, I have a simply supported beam. Let us say this is the beam. and then I have at the center, I have a load which is nothing but RC, and I'm drawing the free body diagram. So this will be RA, this will be RB. Both are hinged or pins, so they don't support any moment. So that's about it. So for this case, and mind you, this is at the center. This distance is L by 2. That is given in the question. And this is L. Now one might, it begs the question, under the action of this roller, when it actually deforms, would it not move somewhere to the right? Which is a natural question that might occur. But since in our assumptions, we are actually idealizing this as a small deformation problem, so we will be applying everything to the initial undeformed coordinates rather than the deformed coordinates. So we will still operate with the assumption that the roller is exactly at the center of C, although this does not create a lot of error. So that is why we proceed with this. But nonetheless, if one were to think about it, naturally this will move somewhere apart from the center, but still we push that under the rug, saying that we are dealing with small deformations. And we will actually see from the values that it is indeed small deformation. Given the section and the length of the members, the deformations or the deflections that come about at our points of interest are much smaller than uh, the actual lateral dimensions of the members. So we are not way off when we are making these assumptions. I hope you are able to see that. All right. So in this case, what is the bending moment diagram like? So this is my bending moment diagram for this problem with this peak. Excuse me. Excuse me. So the value of this peak is nothing but RC L by 4. Why? Because of symmetry, this will be RB and RA will be RC by 2. So RC by 2 into L by 2, which is RCL by 4. So this much we know. So if I were to calculate, again taking this to be a prismatic section, which is given in the question. So this will be nothing but RC by 4EI. So this much I have got. I've got the M by EI diagram. MB by EI diagram. Now, the actual beam would deflect something like that. Let me draw it in red. The beam would deflect something like that symmetrically. That is, I have drawn it a bit asymmetrical. I hope you're able to appreciate. That will actually be a very symmetric curve here. Now, if I take the moment of this diagram about the center point, I will actually be getting this quantity. But that is not the quantity of my interest. I actually want this quantity, which is the deflection at the center of the beam. So here I can see that this is the tangent at this point, and this happens to be the tangent. So the difference between these two is the actual deflection. The sum and substance of this is that I actually need to take the moment of this area of the M by EI diagram about this point instead, rather than the center point. Because if I were to do it about the center, I need to go for 2 steps. Rather, if I, by exploiting the symmetry of the problem, if I take the moment about this end, then I will get the deflection at the center at once. So using the moment area method, in fact, I've already written this. Why don't I take it from there? In the interest of time. Yeah. So using the moment area method, delta 3. Delta 3 is moment of the M by EI diagram about point A in this case due to symmetry. And this is using a single step. Mind you, we still can actually draw this being the tangent at A, So this distance will be theta A into L by 2, and this is what we will get as our TBA if we were to take the moment of the area about this point. The difference of these two will actually give the deflection at the center, but since we are doing it using a single step by taking moment about the hinge, we can calculate the deflection this way easily. So using a single step. So therefore, delta 3 is nothing but the area of this, which is nothing but this is L by 2. So therefore, the area is half into RCL by 4EI, half into base into height into, we know that the centroid of this M by EI diagram is somewhere over here, which is at a distance of 2/3 of the base of the triangle, which in itself is L by 2. So therefore, this is 2/3 into L by 2. So this is half into 0.25 into half into 2 by 3 into half. So this comes out to be, so delta 3 from here comes out to be RCL cubed by EI, and from the coefficients, if I were to calculate this, this will come out to be 1 by 48, which is again one more celebrated expression that we generally remember by virtue of solving many problems. We will pick this up, but actually it comes out to be RCL cube by 48 EI. So far so good. So we have our delta 1, delta 2 from our previous discussion itself, and delta 3 is something we have calculated here. So let us go ahead and substitute it into the compatibility equation that governs this problem. So from here we get this quantity delta 1 minus delta 2 minus delta 2 is not equal to 0, but is some non-zero quantity, and that non-zero quantity is this much, which is RL cube by 48 EI, RCL cube by 48 EI. So now it is just a matter of some manipulation in order for us to calculate this. So let us go ahead and do that quickly. So this will be nothing but, if I take RC common, RCL cubed by EI, let me take it common. So this will be nothing but 1 by 48 plus 1 by 3. So therefore, RC, I can cancel out EI from here. So 48 inverse plus 3 inverse, answer by 8. So RC comes out to be 6 by 17 WL. 6 by 17. All right. So this is the value of RC we have got. Now let us reflect a bit on that. So 6 by 17, that ratio is almost 0.323. This is nearly 0.323 WL approximately. This is for the case where we actually have this beam bending a bit. Now if we were to have this absolutely rigid over the floor, then what was our reaction that was coming? It was 3 by 8 WL. So 3 by 8 is nothing but 0.375. So this is almost 0.375, not almost, exactly equal to 0.375. So what do we see from here? When the floor is absolutely rigid, it offers a higher reaction, whereas some deflection, when it is allowed, when it is placed over a beam in this particular configuration, it comes to 0.323. So these are certain aspects that we can appreciate from viewing the problem. All right, so let us plug in the values. And mind you, this W, as we have seen in the question, pertains to this value, which is 5 kilonewton per meter. And since both the beams are equal, I did not bother to differentiate between this L and this L. But obviously, when we if we were to deal with a problem where these two are different, one must take care that for delta 1 and delta 2, we should be using this L. And for delta 3, since we are dealing with the deflection of this beam, this L is what is supposed to be used. But to make things simpler, in the question, they have given two identical beams. So this did not make much of a difference. So I hope the viewers are able to appreciate that. And this needs to be necessarily accounted for in the problem. So I did not, what I mean to say is, I did not differentiate between these two, these L's and this L. I took these to be the same, but in actuality, this is the length of the second beam, and these are the lengths of the first beam. So, all right. So RC from here comes out to be 6 by 17 into 5 into length is 10. So RC is nothing but into 6 by 17. So this comes out to be 17.65. So RC is 17.65 kilonewton for this problem. Very well. So let us put this where it was asked. So for this problem, RC we have successfully calculated. Now next what is asked is what is the actual deflection at point C, which happens to be non-zero. So we can calculate that using either of this. So since we already know this, so in this question we have been asked what is delta C, which is nothing but delta 3 actually. So this is equal to RC we have got is 17.65 kilonewton into length is 10 meters, length power 3 divided by 48 EI. Now E for this problem is given to be 200. So in fact, let me just take this and calculate EI. So therefore, IZZ is nothing but 200 into 400 cubed by 12 when I convert it to mm. So therefore, EIZZ is nothing but 200 E3 into this quantity. So let me just copy this and put it here. So this quantity we have already calculated. So let us see what deflection at 3 or deflection at C, however we want to call it. So let us see what this comes out to be. So 48 into 200 E3, 200 into 400 cubed by 12 into 17.65 E3 into 10 E3 whole cube. So this comes out to be 1.723 or 1.724 mm. Now, if we were to reflect on this value, we have a beam that is of length 10 meters and merely 1.7 mm is our deflection at point C. So very well. So we have found out what the deflection at point C is. Now the question asks what is the reaction at point A and point D. So we have been asked these two quantities. Actually this should have been, or rather this is B, I think. Yeah, we have been asked what is the reaction at A, what is the reaction at point D. So from the equilibrium of this beam, we can actually calculate what is the reaction at D? Because we already know what the reaction at C is. As for beam AB, we can see that the reaction at C offers a concentrated load at the center of the beam. So by virtue of its symmetry, we can see that RA is nothing but RC by 2. So from the symmetry of the problem, or rather from the symmetry of beam AB, RA equal to RB equal to RC by 2. So this is nothing but 17.65 by 2, which is 8.83 kilonewton. So therefore RA RB equal to 8.83 kilonewton. Very well. So now as for reaction for D, let us draw the beam again. I'll just take yeah. So if I were to take sigma Fy equaling 0, so I'll get RC minus 5 into L, or minus WL I should say, minus WL plus RD equaling 0, or RD is nothing but WL minus RC, which is 5 into 10 minus RC was 17.65 kilonewton. So therefore reaction at D, this is reaction at D, I'm sorry. So therefore reaction at D is 50, yeah, 32 point, thank you, 32.35 kilonewton. So we can see that if that was a fixed end, if the probed support was actually resting on the ground, that reaction is a little bit more, which will get compensated by this reaction. So this has to offer a greater restraint in order for in order to keep that beam in equilibrium, is the sum and substance of this problem. So I hope you're able to appreciate how this came about. It is just a matter of identifying what the governing compatibility equation for the problem in hand is, and then breaking this down into simple problems that we already know and superimposing them, uh, taking advantage of our linear elasticity in order to get to the unknown quantities. So that is how we will be solving this problem. So I hope you're able to appreciate that. So in case there are any questions, please feel free to bring them up. In the meantime, I'll move on. So yeah, so our reaction at D is this much. All right. So let us look at this question now. A circular shaft of diameter D. So we have the diameter of this is given to be D, is subjected to a bending moment MB. So we have a moment like that at the end, which is actually bending the shaft, and a twisting moment of MT. Let sigma y be 250, that the yield stress of the material be 250 MPa, and N equal to 2, where N is defined as the factor of safety for this case. So given these constraints, determine the minimum diameter of the shaft based on maximum principal stress theory. Determine the minimum diameter of the shaft based on maximum shear stress theory. Now we know that generally shafts are designed for stiffness, where we will be getting some value of allowable rotation, and we'll take that as the limiting factor and back calculate the actual section. So this is also a design problem, except that this is based on the pretense that the material will actually fail by exceeding the stresses. And we are using two theories in order to calculate what these will come out to be. Except there is one more peculiarity to this problem is that it is a situation of combined loading. That is, we know we have studied bending separately and we have studied twisting of shafts separately. But in this case, both come together. So let us see how we go about solving this question. So, all right. So let me just draw the shaft once. So I have a shaft like that, which is fixed here. So this is fixed here. Now for this axial, for the bending moment, we know at the free end, this is applied with a bending a moment of 15 Newton meter. Actually, calling this bending moment is actually a bit of a misnomer. It is actually an externally applied moment, which will induce bending moment at in the shaft. So at any section when we cut, the internal response is what is bending moment. Actually, calling this MB is it's a bit of a stretch, but I wanted to actually clarify this. So let us take our sign convention like this. So for the positive bending moment, let this be the sign convention that we adopt. And for my twisting moment, so I may well have drawn this again. Okay. So for the positive twisting moment, let this be the sign convention that we adopt, with the understanding that this is the positive surface, this is the negative surface, however the coordinate is. So for the beam, we have generally seen that for beam analysis, for bending analysis, we have generally seen that the axis of the member is taken to be the x coordinate, and then z and y come about using the right hand rule. Similarly, for shafts, it was convenient for us to represent that in the cylindrical polar coordinates, where we took the axis of the shaft to be z, and then at any point was characterized by r and theta. So it's a matter of convenience, but we will see towards the end how to club these two together, given the fact that for beam analysis, the x direction, which is along the axis of the member, is same as z for our twisting analysis. So based on the similarity of these two axes, we'll actually be able to simply populate the stress tensor and then see how to go about designing this shaft. So that is the sum and substance of what we are going to do. So let us go ahead and do that. So here at the free end, I have a moment of 15 kilonewton applied like that. So let me just apply it like this. So M is nothing but 15 Newton meter. All right. So at any section, if I were to cut a section, so this has exposed the negative face. So in the negative face, this is my bending moment. So therefore, equating moment about z equaling 0 by virtue of this being in equilibrium, what do I get? Minus mb plus m equaling 0, or mb is actually equal to m, which is equal to 15 Newton meter. In fact, let me write that down, which is equal to 15 Newton meter. So at any section, the bending moment is constant. It's sometimes easier to do it using our first principles, so that we can always get back to them when we need it. So we have determined the bending moment at any section, which happens to be constant, which is 15 Newton meter. So far, so good. Now I know that stress in the case of bending can be given by our flexure formula, which is sigma x is minus mb by izz into y. So this much I know. Now For this shaft, the bottom portion will be in tension, the top portion will be in compression. So for the maximum stress, so therefore for maximum bending stress, Y will actually be equal to d by 2. I am just taking the diameter d divided by 2. So for the circular, that is the distance of the farthest fiber from the neutral axis. So therefore sigma x max in this case is minus mb by what is izz for a circle where z is pointing out of the plane of the paper, where z is actually like this. I'm sorry, we have the section like that. For the bending analysis, I should in fact for the bending analysis my axis is like this. So this is the x-axis, and then I have y, and z is coming out of the plane of the paper. So let me just draw it like that, z. And when I look at it in the cross section, I have x is coming out of the plane here. This is y, and this is z. So this is what our axes look like when we are considering flexure. So in this case, what is izz? It is nothing, actually it is nothing but half of the polar moment of inertia of a circle, which is nothing but, yeah, pi d power 4 by 64, exactly. So this is pi d power 4 by 64 into y max we saw is d by 2. So therefore sigma x max comes out to be minus mb by pi d cube, and this will be 32. So minus 32 mb by pi d cubed. So we have got a general expression for that. So let us keep that as it is for the while, uh, for the time being, and let me take a point at the bottom. In fact, so given the positive bending moment here, if I were to take y as minus d by 2, let me take this to be minus. So my actual stress will come out to be tensile, which is positive. When I take this as minus, it is just a matter of getting the actual maximum tensile stress. So far so good. So actually I have taken a point over here. In fact, why don't I mention it here? So at this point, y is minus d by 2. That is what I have substituted, and I have got what the expression for the maximum stress over there is, which is pointing in the direction out of the plane of the screen when I look at the cross section along x. I hope you are able to appreciate that. And this is caused only by bending. So far we have looked at the bending action alone. Now we will be looking at the twisting action. So let me again take this section here. In fact, I should say here this is bending of the shaft is what we discussed so far. Now let us discuss twisting of the shaft. All right, so let me erase what is given here, and let us revisit the question on how the twisting moment is actually applied. So yeah, we are able to see if we were to hold our hands in such a way that it curls up with the actual twist that has been applied. So we can see that the axis, the thumb, would actually be pointing in the direction, in this direction, in minus z direction. So let me replace that moment, the twisting moment, like that. So this is my mt, which is equal to what is the value, which is equal to 20 Newton meter. Again, we should not be, we should actually be calling this an applied torque, which will induce twisting moment at any section, depending on our twisting moment diagram. So this is nothing but 20 Newton meter. So as we did for our bending analysis, let us go ahead and draw a free body diagram. So let me take a cut section over there, and using this sign convention, I'm sorry, just a moment. There is some issue with the touch. Yeah. So I had used this sign convention here in order for me to calculate the bending moment. Similarly, I'll be using the sign convention for twisting moment diagram here. And I know this is a negative surface, so I'll just put this here. This will just be M, and this will be MT. So sigma F or sigma M about Z, and Z is this in this case. I hope you are able to appreciate that. Let there not be a confusion when we consider bending and when we consider twisting. It is just a matter of convenience about how we represent these axes. When we are dealing with twisting of shafts, it is a general notion that we will go about analyzing this in cylindrical polar coordinates, where the axis of the member is taken to be Z. At any point, we will have R, and we will have theta that is perpendicular to that. But for bending, the axis of the member is taken to be X, which is same as this, and then Z and Y and Z come about as we discussed earlier. So I hope there is no confusion in that. So equaling 0 gives us minus MT minus M equaling 0, or MT at any section is minus M, which is minus 20 Newton meter. So we have actually got our twisting moment at any general section, which again happens to be a constant. So far so good. And for twisting, we know that our tau z theta at any section where the plane is characterized by z in the direction of theta, we have our tau z theta equaling for a solid shaft, we know it is actually mt by ip into r max. So R max is nothing but d by 2. So this we already have seen when we were dealing with problems of twisting of shafts, design of shafts, which was 16 mt by pi d cube. Because ip will be pi d power 4 by 32, and this will be d by 2. So that is how this comes about. So, and I have to account for this negative here, or let me not account for that now. When I plug it in the final values, I'll account for that. All right. So we have got what is the action in terms of stress for the twisting part, and as for the bending part, we have actually got the normal stress at any section. Now we have to populate the stress tensor at some point. So let us go ahead and do that. So yeah, as I'm sorry, just a moment. Yeah, there seems to be some issue with the touch, that's why. Okay, so for bending analysis, we saw yeah, so this is for our bending analysis. Similarly, for our twisting or torsion analysis, or howsoever you want to call it, we have this as Z, And then we have in any direction, this is r, and we have the perpendicular to that, this is theta direction. Now if I were to take the same shaft and the same point, in fact, so I know here the axis that is pointing out of the plane of the paper is actually z for the case of cylindrical polar coordinate. If this outside is z, I have this as my r for this point, and this will be my theta. So r cross theta will actually bring about z that is coming out of the plane of the paper. So let me just draw this. So this will be my r, this will be my theta, and r cross theta is r cross theta is z. I hope you're able to see that. So this is just an axis I have drawn. So from these two, the orientation of the axis, at this point I can see that actually x and z are parallel to each other. They are one and the same. So in this case, I have my stress tensor as sigma xx, sigma xy or tau xy, however you want to call it. Let me call that tau xy, sigma yy. But actually speaking, this I can also populate as sigma xx was this quantity. So I'll just delete this. And I actually took y to be minus y by 2, which is why this came out to be positive. So this is my actual stress tensor here. So this is 32 MB by pi d cube. That sits at xx. And then I have, by virtue of that being a free surface, I don't have any shear and I don't have any sigma yy as well. So this is also 0. So this is the stress tensor in the xy coordinate at this point for this problem. Similarly, if I were to populate the stress tensor due to just the twisting action, I saw that tau z theta is this quantity, and this is a case of twisting of a shaft, which happens to be a case of pure shear. So there will be no normal stresses. So let me just populate the stress tensor here in the z theta plane. So I will have sigma theta theta, sigma theta z, or rather tau sigma theta theta, tau z theta, or just equality of cross shears I'm using here, and then this will be sigma zz. This is the general form of the stress tensor, but for this problem it will water down to, this will be 0, this will be 16 mt by pi d cubed by equality of cross shears, and this is also 0. I hope you're able to appreciate how we have populated these two stress tensors. Now, by invoking the fact that x-axis in bending analysis is parallel to z-axis in twisting analysis, so sigma xx of bending can actually sit at the place of sigma zz of twisting. So if I were to combine these two, this sigma zz with z-axis pointing in this direction is same as sigma xx with x pointing in the same direction. So I hope that is the sum and substance of what I'm trying to communicate. I hope you're able to see it all right. So what the stress tensor will be is, if I were to take this here, this is sigma theta theta, which still remains 0. However, for this quantity, I just need to place this here. So this is the stress tensor for the case of combined loading. Combined loading meaning bending as well as twisting, expressed in the theta z coordinate system. So that is all there is to it. So now we have actually, this will be MT and that is MB. So we have actually found out, under the action of the combined load, if I were to take this point, what does my stress tensor look like? So it has components of the twisting moment as well as our bending coming into the picture. So now that I have arrived at the stress tensor here, what does the question ask me to do? It is asking me to design based on the maximum principal stress criteria or the maximum shear stress criteria. So now we have a stress tensor with components that are coming in from the actual problem, meaning MT and MB and so on. So we have populated the stress tensor. So the next logical step is to actually calculate the principal stresses. So we are able to see for this. Yeah, yes, please go ahead. Yeah,
Sorry
yeah,
to bother you. So when you say theta z coordinate system, so that is equivalent to
yes, yes.
the z is equivalent to the x in the bending coordinate system, correct? So I'm not sure I understand why
Yeah,
it
so
went to
this is
the
sigma theta theta and
um,
sigma zz. So I
so
have
we have
just take,
sigma
yeah,
theta. Right, right. The other one was equal
okay,
to
okay,
right.
yeah,
Yeah,
all right.
yeah, yeah. Understood, understood.
So now that we have
Sure.
this, we can
Thank you.
clearly see for the stress tensor, there is some non-zero shear. So these are the diagonal elements are not the principal stresses. So let us go ahead and calculate the principal stresses. So calculating the principal stresses for this case, we have sigma 1, or rather sigma theta theta we have as 0 in this case. Sigma zz we have as this quantity. And then we have tau theta z or z theta, however you want to call it, as this quantity. We know how to calculate principal stresses in this plane, which is sigma 1 comma 2 is, it is this by 2 plus minus root over the same thing except for a minus in the middle, the whole squared plus this quantity, the whole squared. So this is just coming from our transformations. So this much we know. So let us knock off the terms that are 0 here. So I don't have sigma theta theta existing in this problem. So this is sigma zz by 2 plus minus, again this quantity goes to 0. So I may well drop the minus sign here because it is getting squared. So this comes out to be, this comes out to be the simplified version of that. So let us substitute this. We know that sigma zz is this much and tau z theta is this quantity. So on substituting, what will we get? Sigma 1 comma 2 is sigma zz is this by 2. So this will just be 16. It will become 16 plus minus root over again the same quantity 16 whole squared plus tau z theta is again a 16 whole squared. Very well. So sigma 1 comma 2 is I can take 16 by pi d cubed. If I take it common, I am left with mb plus minus again this quantity is getting squared inside inside root over, so that comes out again and I've taken that common. So this will leave me with mb squared plus mt squared. So this is my, or rather let me again split it up and write it so that it becomes clear. So from here I can see that sigma 1 is 16 by pi d cubed. So therefore sigma 1 is 16 by pi d cubed into this quantity, except there will be a plus. Similarly, sigma 2 is the same quantity with a minus. So we have got sigma 1, sigma 2 here. Now we have to calculate, we have to actually design the shaft by actually obtaining its minimum diameter based on the maximum principal stress theory. And for this question, we have been given that for the material under uniaxial tension, sigma y, that is the yield stress, is 250 and the factor of safety is supposed to be taken as 2. So what this means is, by using this theory, the maximum principal stress theory, so design based on the maximum principal stress theory states that sigma 1, which is algebraically the highest, is less than equal to sigma y by some factor of safety, or I should say the factored sigma y. This is my condition for that. So I can take this is less than equal to, I know that sigma y was 250 and the factor of safety was 2, I suppose. It was something, yeah, factor of safety is 2. Now what is the unknown here? We know what MB is, what MT is. MB came out to be, for the problem, MB was, we calculated it somewhere. Yeah, MB is 15 Newton meter and MT is minus 20 Newton meter. But since MT is getting squared, doesn't matter. So it is 15 and 20 is what we need to plug it in here. So let us go ahead and do that. So this is 16 by pi d cubed into 15 Newton meter plus root over 15 E3 squared plus The other quantity was 20 or 25 is my question. It is 20. So this is 20 E3 squared, which has to be less than equal to this quantity. So from here, I can quickly calculate this. 16 into 2, 32 by 250 pi into this quantity is d cubed, or 15e3 plus root over 15e3 squared plus 20e3 squared into 32 by 250 by pi. So 1629, cube root of this is around 11.76. So I encourage the viewers to calculate this on their own once. So D 11.76. All right, great. Thank you. So this will be greater than equal to 11.77 mm. So we have actually, what have we done? If we were to reflect on the problem, we have a problem where we have a circular shaft of some unknown diameter, which is what we are supposed to determine. We have been told that under its operating conditions, it is subjected to a bending moment, or it is subjected to a moment causing bending of 15 Newton meter and a twist or a torque of 20 Newton meter in this nature, and given some constraints and the material properties and some factor of safety, according to the maximum principal stress theory, our minimum diameter of that shaft should be 11.77 for it to be uh, operating under safe conditions. So let us go ahead and do the same with maximum shear stress theory also. So for the maximum shear stress theory, what is the condition? We had written it somewhere. I'll take it from there in the interest of time. Yeah. For the maximum shear stress theory, copy. This was our condition. And except there we were talking about failure, here talking about safety, so it should be less than equal to this for it to be safe. So if we were to see our values, which will govern is sigma 1 minus sigma, this is what will govern. So actually it will just be half. So this will be sigma 1 by 2 would be less than equal to sigma y under uniaxial tension by 2 into the factor of safety, which also happens to be 2. So therefore, this is sigma 1. So this is less than equal to sigma y is 250 into 2 into the factor of safety is again 2. And this also I have to divide it by 2. So let us quickly solve this, what this comes out to be. So I'll just remove. So let me remove this 2. So this is 125. And let me take d cubed over there. So this is nothing but 16 by 125 pi into what was the value? This quantity. Which is less than equal to d cubed, or t is greater than equal to 15E3 plus root over 15E3 plus 20E3 into 16 by 125 pi. Cube root of this comes to 11.76. Is it coming out to be the same? Okay, some issue somewhere. Anyway, I leave it to the viewers to plug it in and actually find out what the value is. When I post the sheet, I'll ensure that the answers are consistent. But I hope how you are able to how we are able to actually arrive at the design or the dimension of the shaft given some theory, given some constraints of the material. So I hope to that end I've done some justice in explaining this. So let me move on to the next problem. A thin steel pressure vessel with closed ends is subjected to an internal pressure Pi. So we have a pressure vessel subjected to internal pressure and two strain gauges. So at far away from the ends, we have two strain gauges. And as we discussed earlier, that since we cannot stack it one over the other, the strain gauges, it's a T rosette which is pasted with some small distance between the point, but with the understanding that this strain gauges A and B are actually measuring strain at that very point in those in along their gauge length. So strain gauge A is actually measuring strain along that direction, and strain gauge B is measuring strain along that direction. So has two strain gauges pasted on the outer surface of the uh, vessel in the direction shown. So it is pasted on the outer surface, and we know that the outer surface is actually free. So there is no traction applied on the outer surface, which means we have one stress. Sir, is X axis bending always parallel to Z axis in twisting? Yeah, actually for any section, we have a member like this. When we consider this to be bending, our axis that we take along the axis of the member, that is along the length of the beam, the axis that we take is X. And then Y and Z become the coordinates in the cross section. Whereas if we were to consider the same thing when we view it from a twisting point of view, we replace this with Z, and then the cross section won't have Y and X, but it will have R and theta. So R theta Z, where Z is the length of the axis along the length of the member, and then XYZ, where X is the axis along the length of the member. This we actually do for our convenience, because generally when we go for twisting, we will be dealing with circular shafts which are better represented. The boundary conditions are easily represented in the cylindrical polar coordinate system rather than our XY. That is why we do it. But yes, when we come to the length of the member, one axis is termed X in case of bending. The same axis we will be uh, representing that as Z in the cylindrical polar coordinates for twisting. I hope I hope it's clear. Okay, fine. All right. So we are actually dealing with the strain gauges that are pasted on the outer surface, which happens to be a free surface, which is a point to be noted here. Uniaxial tension test conducted on the material batch reported that the onset of yielding was at 415 Newton. So the material with which this shaft is made, with this pressure vessel is made, was tested under uniaxial tension, that batch, and it was found that yielding sets on at 415 MPa. It is proposed to check the safety of this pressure vessel under operations by increasing the pressure and measuring the strains using the strain gauges A and B shown. So we can increase the pressure, we can also attach a pressure gauge and actually find out what the pressure is. We are going through another route where we actually paste the strain gauges in the known principal stress direction. So at this point, we know that one of the principal stresses is along this direction and the other principal stress is along this direction, which is nothing but hoop and longitudinal stress for our closed cylinder, closed pressurized cylinder. In such a case, when we already know the principal stress directions, we can just do with two strain gauges which are aligned along those two directions in order for us to be able to populate the stress tensor and subsequently the populate the strain tensor and subsequently arrive at the stress tensor, which is what they seem to have done. So based on the measures of the strain gauges A and B in the direction shown, they are trying to find out, back calculate what the pressure is inside the pressure vessel and whether it is operating under safe conditions by specifying certain limits. What are those limits? In this question, it says the onset of yielding based on Tresca yield criterion. Tresca is nothing but maximum principal stress, the maximum shear stress criterion. So if we were to design or rather analyze this shaft by considering failure to set in when our Tresca yield criterion is used with a factor of safety of 1.5, our idea is to find out whether it is operating under safe conditions or not, given that the material yields at 4 and 5 and whatever be the values of our A and B. So, all right. So with this background, let us try to approach this problem. So we know for this case, oh, I'm sorry. Okay, at this point, let this direction be taken like that. Let this be the x direction and let this be the y direction. Z direction is pointing out of the plane of the paper. Although this direction business here is not very important, I'm just for convenience, I'm just putting it this way. One might ask that this is circular, why don't we represent it with r theta z coordinate system? We may well do that. It bears no consequence as such. All right. So sigma xx is actually sigma longitudinal stress here. I hope we are able to see that when we cut this, we will have sigma long here and the pressure will be pushing against it. So when we actually take equilibrium of that, we will be able to arrive at what the longitudinal stress would be. Similarly, if we were to cut it this way and view half of the cross section like that, we will be having hoop stress here and we will be having pressure acting like this, which will balance out, which we have done umpteen number of times in the previous sessions. So I'll avoid delving into that. So this is sigma yy is nothing but sigma hoop. And at the surface, sigma zz is actually 0 because by virtue of that being a free surface. So we already know what the principal stresses are. We know that sigma hoop is nothing but pi r by t, where r is the mean radius of the pressure vessel and t is the thickness of the sheet that is being used. So r here is actually 400 by 2, which is 200 mm. Technically, it will be 200 plus 3 by 2, but it doesn't make much of a difference here. So R and then thickness will be 3 mm. So R and T we know, and this is pressurized with Pi inside. So sigma hoop is actually PR by T. I hope there is no confusion as to how this came about. This comes from equilibrium of the cut section where we expose the hoop stress, which we have done in one of the previous sessions. So I encourage the viewers who are finding it hard as to how this came about to please revisit that session. Similarly, we know that hoop longitudinal or the stress longitudinal is nothing but Pi r by 2t. So these are the principal stresses. We know this is higher than this, so therefore sigma hoop is sigma 1, sigma longitudinal is sigma 2, and sigma 3 is 0 for this case. because that is a free surface. All right, so now that we know the three principal stresses, let us see what the question is asking. Determine the value of the pressure P at the onset of yielding based on Tresca yield criteria, where the factor of safety is 1.5. So let me just get Tresca yield criteria from wherever we had put it. Oh, I remember having put it somewhere. Yeah, copy. So this is Tresca yield criteria. So the at the onset of yielding, we are looking at the limiting condition where these two are equal. So therefore, this is nothing but maximum of PR, PIR by T minus PIR by 2T. This is PIR by 2T minus 0, and this is 0 minus PIR by T, which would be, here we should not forget the factor of safety that we are talking about, and this yielded us at 415, and the factor of safety is, I think, 1.5. Yeah, so this is 1.5. So it is easy to see that this would actually be the maximum of the two, sigma 1 minus sigma 2. Oh, I see what the issue is actually. Why the answer for the previous question, this was not coming because there is a half missing here. Yeah, okay, these are there. I think I did not account for it here, I suppose. Yeah, so I have a half floating around here. So I hope that is clear now. All right. So this will come out to be PIR by 2T equaling this quantity at the onset of yielding. So our Pi is nothing but 415 into 2 into 3. 3 is the thickness T divided by 2 into 1.5 into R, which was 200 mm. So this comes out to be 415 into 6 by 2 into 1.5 into 200. So this comes out to be 4.15 MPa exactly. So Pi is 4.15 MPa at the onset of yielding according to Tresca yield criteria with a factor of safety of 1.5. So far so good. So this we have been able to calculate. So let me just put it here. So what does the next question ask us? It asks determine the strain epsilon A at the onset of yielding based on this criterion. So we know at this criteria, using this criterion, what is the pressure that would have transpired and at the verge of failure, our defined failure. So therefore, at failure, Pi is 4.15 MPa. Now we know that our hoop stress would be, it's an overkill to write it time and again. I'll just take it from here. Our hoop and longitudinal are these, right? So we know hoop is this, epsilon is this. So therefore, epsilon A, in the question, we can see that A is actually pointed in the longitudinal direction. So its main component will be longitudinal, and because of Poisson's effect, the hoop stress will also contribute to the strain. So this will be nothing but Pi r by 2T E minus mu Pi r by T E. Is there any confusion of how we have written this? What I have done is nothing but sigma 1 minus mu sigma 2 by E. Sigma 1 by E minus mu by E sigma 2. That is all I have written here for epsilon A. So therefore, epsilon A is nothing but Pi r by Te into half minus the Poisson's ratio. And we know that Pi is 4.15 MPa, thickness is 3 mm, E is must be given in the question somewhere. For the material, E is given to be 210 and mu is given to be 0.3. So let us go ahead and substitute that. So this is 210 GPa, mu is 0.3, R we know is 200 mm. So therefore, epsilon A is nothing but P R by Te T E into half minus 0.3. So therefore, what does this come out to be? 3 into 210 E3, 4.15 into 200 into half minus 0.3. And naturally, in the question, we have been asked to report this in microstrain. So I just have to multiply this by 10 power 6 in order for me to report this in microstrain. So this comes out to be 263.5 microstrain. So if our theories are correct, or rather close than our approximations, uh, we will be able to see that at the onset of yielding, as we define it, at that pressure, our strain gauge will actually be reading 263.5 microstrain, which will never happen, actually speaking. It will be off by some amount because of many approximations that have gone in. Not only that, our strain gauge instrumentation itself picks up error if it is not, if we have not accounted for temperature and things like that. But in theory, as engineers, we should know what is the ballpark figure that we should expect and then reason out what this deviation is caused by. So that is the essence of uh, this question. So epsilon A will come out to be this. What is epsilon B be? What will epsilon B be? So it is, I'll just quickly write it down. Epsilon B is nothing but I just need to shift around this 2 because this will be the main, I'm sorry, this is epsilon B, which is along the hoop direction. So the hoop stress contribution and our longitudinal stress causing the Poisson's effect. So this will come out to be Pi. P is 4.15 into R by T E into 1 minus 0.3 by 2 into 10 power 6. So epsilon B will come out to be 3 into 200 E3 into 4.15 into 200 into 1 minus 0.3 by 2 into 10 power 6. So this will come out to be 1175. I encourage the viewers to check this on their own once. So this comes out to be 1175 microstrain. 1175. Very well. Thank you. All right. So now that we have done this, let us move on to the next question. We have been asked to do the same thing, except our criteria is different now. It is the von Mises criteria. So what is the von Mises criteria? This is related to the octahedral shear stress, which is again some form of some constant into the invariant. It is related to the second invariant of the deviatoric stress tensor. You can look that up as to how these are related, but basically I'll just be putting the expression here so you can derive this on your own and see for yourself once. So this will actually be our expression for this, except when we are dealing with a factor of safety, then the entire thing will go inside the square. So let us plug this in. So we know that sigma 1 is PIR by T, sigma 2 is PIR by 2T, sigma 3 is 0. So I'll just plug this in. These two will be nothing but PIR by 2T. I'm sorry, just a minute. PIR by 2T, the whole squared, plus sigma 2 minus sigma 3 by 2. All right. And then this will be PIR by T, the whole squared, the entire thing into half less than equal to 415 is when our yielding was setting in, divided by our factor of safety, the whole squared. So it is just a matter of calculating Pi from here. Rest everything is known. We can take Pi common and we can calculate that. Once we calculate what Pi is, we have to do the same drill to calculate epsilon A and epsilon B using the concept of generalized Hooke's law, which we did, except this Pi, which we will plug in now, will be coming from a different criteria, which is von Mises instead of our Tresca criteria. So I will leave it to the viewers to solve this on their own once. And anyway, when I will post this sheet, I'll ensure that these values are filled in. All right, great. So with this, I have run out of questions and we have also run out of time. So in case there are any questions about what we discussed today, I'm happy to take them now. I hope I've done some justice into explaining how the application of the superposition method, etc., comes about. And we also saw some rudiments of theories of failure as to why we need them, how to apply them, and how we can also be sensitive to which criteria to choose and which will give a conservative result and so on. So at this juncture, if there are any questions, I'm happy to take them now. Otherwise, we can call it a day and we'll perhaps meet next week, same time, to discuss the contents of week 12. Following that, the week after next, we will be having a comprehensive session of which will cover many solved examples from week 1 to week 12. And also we can take up any questions there are from the viewers so that you get an all-rounded exposure to the subject matter before taking the exam, for those of you who are taking the exam. So I have nothing more to say. If there are any questions, please feel free to ask. Okay, all right. Okay, so I hope today's session was helpful for you in some way. So let us wrap it up then. I'll see you guys next week, same time, to discuss contents of week 12. So till that time, thank you for attending, and I'll see you around. Bye.